afternoon everyone. I am Dr. Anuradha from Lady Shri Ram College for Women, University of Delhi. Welcome to the lecture series conducted by CEC-UGC. Today I am going to talk about two measures of central tendency, namely arithmetic mean and median. I have already talked about the arithmetic mean in my previous lecture, where I told how we can define arithmetic mean and then how we can find the arithmetic mean when we have a raw data, when we have frequency distribution, when we have data in which we change the scale and then we change the scale as well as origin. So to start off, I will once again start with the same definition, that is we have 5 main measures of central tendency or averages. Average is the value of the variable which is representative of the entire distribution. The following are 5 measures of central tendency: arithmetic mean, median, mode, geometric mean and harmonic mean, and I am going to basically concentrate on the first two, namely arithmetic mean and median. Before I go on to start and discuss about arithmetic mean in detail, I will do certain proofs also regarding the properties of arithmetic mean. There is one symbol that will appear very often in your textbooks or wherever you study statistics, which is the symbol of summation, that is called capital sigma. Now first I would like to elaborate how we can use this capital sigma, because if we don't understand how this capital sigma is made, what it means, how we can simplify this capital sigma, then it is very difficult to proceed through the study of statistics after a certain stage. So when we have expressions involving finite sum or infinite sum, then we need to use the symbol capital sigma so that we can represent the expression in a compact manner. The very simple example if I take, suppose if I have to talk about the sum of first 10 natural numbers. So if I will say 1 plus 2 plus 3 plus 4 plus so on 10. So here we have already used one particular way of saying plus so on. Now when we are having a proof where we need to get this sum of first 10 natural numbers, then I will use this symbol capital sigma appropriately, so that that sigma along with the term on which this summation works with the range of the variable over which this sum can be carried out, then we can represent that sum of first 10 natural numbers, sum of first 15 natural numbers, or sum of natural numbers where we don't even have the upper limit, it goes up to infinity, then we will use this symbol capital sigma. So first we need to identify two things. One is the ith general term, which will appear here, after summation this will appear here, the ith general term will appear, and then you have one index variable I, which will vary over a range. So the range of I in fact symbolically means the range of the summation. So now we will use the summation symbol sigma with the index variable I defined over a range and the ith general term. Any quantity which is independent of I can be taken outside the summation. So that means the terms that I will write over which the sigma is operating, then we have there are certain terms which are dependent upon I and there are certain terms which are independent of I, and then those can be taken outside the summation. Let us just understand them with by the means of certain examples. Let us look at the sum S, which is 2 into 1 plus 2 plus 3 up to so on plus n. That means it is 2 plus 4 plus 6 plus 8 plus so on to n. Now instead of writing this sum laboriously at every step in the proof or wherever it occurs, what we can do is we can write them in a compact manner. And how do we write in a compact manner? We write it in a compact manner by looking at this, putting this sign of capital sigma. How many terms are there? We can see clearly the terms are 1, 2 up to n. So we need the sum over n terms. So what I am going to do, I am going to use capital sigma, and then I am going to take the index variable I. Now this index variable I can be I, j, k, u, v, any variable. It doesn't need to be necessarily only the the I can only be used. So here I have taken I. So now I will take value from 1 to n. What it is meaning is that this sum involves sum of n terms. Now n terms, sum of which n terms? Those terms are given by here by 2i. So what we do basically is look at this expression. I look at its ith term. So ith term here is 2i. Therefore, we have located first the ith term, then we have taken the capital sigma over the range of I, which is I going from 1 to n. And here, therefore, this is the compact notation which denotes this sum S. Now, as I have already commented, since 2 is independent of I, so it comes out of the summation sign. So, it is equal to 2 times summation I equal to 1 to n I. Therefore, this is the expression with which I am going to work. Let me take I will take few examples so that you can understand that sums. So, here let S1 be equal to x1 plus 2x2 plus nxn, then here the ith term will be, see, if I take I as 1, that is 1 into x1, I as 2, then 2 into x2, similarly ith term will be I into xi, and like that you go on till n into xn. Now, here we can represent this S1 sum as, now first I will write this summation symbol, then I will take an index variable over the range of the sum. So, sum is going from 1 till n. So, j I have taken now here j as my index variable. So, j is running from 1 to n, and then I have terms j into xj. Similarly, another example, here as I said, we don't need to have the finite sum, we can have infinite sum also. So, let S2 be equal to x1 plus x2 plus x3 plus x4 and so on. Then we can write S2 as equal to summation k equal to 1 to infinity xk. So, here what it means, I have looked at the kth term which is xk, and then my sum is going from k equal to 1 to infinity, that means it is an infinite sum. Similarly, let us take one more example. Now, sometimes if the sum is given to you, you can also find you can operate the capital sigma over the term and then find the sum. So, it works both ways, either you are given a sum and you are using the capital sigma to express that sum, or sometimes you are given the terms in terms of capital sigma and you are expected to give the value of the sum. So, let T be equal to summation L equal to 1 to 5 2L plus 1 into L square. Now, here I can clearly see that there are how many terms we are summing? We are summing 5 terms. And how do we open it? We first take the value of L as 1, then we take the value of L as 2, then we take L as 3, and so on we go to L as 5. So, when I take L as 1, the term inside becomes 2 into 1 plus 1 into 1 square, which is 3 into 1 square, plus then when L is equal to 2. So, 2 into 2 plus 1 5 into 2 square, so 5 into 2 square. Similarly, when I take L as 3, then it is 7 into 3 square, plus when L is 4, 9 into 4 square, and when L is 5, 11 into 5 square. So, when it's very simple calculation, T comes out to be 505. So, this sum that I have written in the compact notation actually has the value 505. Similarly, I can go to one more example, that is, suppose I have S and now I can always have terms involving more than one variable. So, here suppose we have xi as well as yi. So, what we are going to sum? We want to sum 2xi plus I into yi over the range I equal to 0 to n. So, that means there are n plus 1 terms here starting from I equal to 0 going up to n, and the expression has 2xi plus I into yi, which I have to sum. When I am doing the proof, what we can do is we can simplify this sum, as you must have done till 12th level, that when you have integral of fx plus gy fx f1x plus f2x dx, then you can do integral f1x dx plus integral f2x dx. You can separate the integral and then operate the integral separately and get the expression. Similarly, here this kind of thing works. You can actually now operate this capital sigma separately over 2xi plus capital sigma over I into yi. So, see, this is what it will become. So, now S can be written as summation I equal to 0 to n 2xi plus summation I equal to 0 to n I into yi. Now, in the first term, since 2 is independent of I, therefore, it has come outside the summation, and I can straight away write S as equal to 2 into summation I equal to 0 to n xi plus summation I equal to 0 to n I into yi. So, if I hope that through these examples you are now comfortable in writing the summations, and then as an exercise you can take certain sums and try to represent it through using this symbol, and then you will understand what I have been meaning to teach you. Now, I have already introduced arithmetic mean in my earlier lecture, but still I will again, just for the sake of continuity, I will again start with the definition of arithmetic mean. It is a measure of central tendency of a finite set of observations. Specifically, it is the sum of the observations divided by the number of observations. So, we will denote the observations by x1, x2, x3 and so on, and then my x bar is given by sum of the observations, which is sigma I equal to 1 to n xi by small n. I hope now you understand what this my sigma I equal to 1 to n xi means. It means x1 plus x2 plus x3 up to so on plus xn upon the total number of observations, which is n. Now, this was the formula when you have raw data. But suppose you are given the frequency distribution, that means you are given the data has been grouped into the either grouped into the class intervals, or you have a frequency distribution of a discrete variable. Then we denote that by xi fi I equal to 1 to so on n. Again I will repeat, when your capital X is a discrete variable, then this small xi will mean the values of capital X, and small fi will mean the number of times each value of xi is repeating, that is frequency of the ith value of x. So, here I will be given x1, x2, x3 so on xn and corresponding f1, f2, f3 so on fn. So, that is the case when you have a discrete frequency distribution. But suppose you are given the frequency distribution which is grouped into the class intervals, in that case my xi will mean the class mark, and which I obtain by adding the lower limit and upper limit and dividing it by 2, and fi is the frequency of that particular class interval whose class mark is xi. So, here then my n will be the total number of class intervals. So, when we are given xi slash fi, which is either the discrete frequency distribution or continuous frequency distribution, then my x bar is x1 f1 plus x2 f2 plus so on xn fn upon f1 plus f2 so on plus fn, and which again I hope now you can clearly write it very easily using this capital sigma, that is summation I equal to 1 to n xi fi upon summation I equal to 1 to n fi, and this sum of frequencies is the total number of observations that you have in the data. So, that we denote it by capital N, and the numerator remains as it is. So, now we will start with the certain properties of arithmetic mean. Rather, I will discuss in particular 3 properties of arithmetic mean. So, let us talk about the first property. The first property is that algebraic sum of the deviation of a set of values from their arithmetic mean is 0. That is, if I am given the frequency distribution as xi fi I equal to 1 to n, then summation I equal to 1 to n fi into xi minus x bar is equal to 0. So, I will just try to explain it in a simple way what it means. So, suppose x1, x2 so on xn are the n values of a discrete variable. I will first obtain its mean, arithmetic mean, which is say x bar, and now I have to look at deviation of each value of x from x bar. So, that means what will I have? I will have x1 minus x bar, x2 minus x bar, x3 minus x bar and so on, xn minus x bar. And when we have that, each of these xi is repeated fi times. So, that means the first x1 minus x bar will be repeated f1 times. So, therefore, when I am trying to get the algebraic sum of all the deviations, what I have to do is I have to multiply x1 minus x bar with f1. So, it will be f1 into x1 minus x bar plus f2 into x2 minus x bar and so on plus fn into xn minus x bar. And what this property says, it says that when you have such an algebraic sum of the observations from its arithmetic mean, then the sum I equal to 1 to n fi into xi minus x bar is 0. In case you are given the raw data, then fi will be 1, and therefore it will be summation xi minus x bar will be equal to 0. Now let us do it through the proof, because proof is an important part of statistics discipline. Unless we don't understand the proof, we don't understand really from where the things are coming. So here I will start with my left hand side, which is summation I equal to 1 to n fi into xi minus x bar, and I have to establish that this is equal to 0. So what I will do is, as I have told you earlier by means of an example, that I can always separate the terms. What I can do is, I can multiply fi to each of the term xi and x bar. So I can write this as fi xi minus fi into x bar, and then I can separate the sum over the two terms individually. So then it leads me to this expression, that is equal to summation I equal to 1 to n fi xi minus summation x bar into fi. Now understand that x bar is the mean which is based on all the observations, rather all the n observations. So therefore here your x bar is a fixed quantity, it is not varying with I. Therefore this x bar which was supposed to come here comes outside the summation, and I will have summation fi xi minus x bar times summation fi. Again, earlier we have introduced sum of the frequencies, sum of all the frequencies rather, is denoted symbolically by capital N. So I will straight away write capital N for this sum. So therefore it becomes summation fi into xi minus x bar becomes summation fi xi minus x bar into capital N. Now let us use the definition of x bar. The definition of x bar says x bar is equal to summation xi fi upon capital N. From here I will get the value of this summation. The numerator will be equal to actually x bar into n. I just cross multiply this capital N with x bar. So we get summation fi xi as equal to x bar into n, and understand this value of summation xi fi, I put it in this expression, then it becomes x bar into n minus x bar into n, which is actually equal to 0. So we have established the first property, and now we will move on to the second property. The second property says the sum of squares of the deviation of a set of values. So understand, whenever I talk about a deviation, it means look at your x1, x2, x3, so on, xn, and subtract each of x1, x2, x3, xn from subtract this from some quantity. Some quantity should be subtracted from each of the xi's. That is what I mean by deviation. So it is saying, so I will read out again, the sum of squares of the deviations of a set of values is minimum when taken about its mean. So what I mean to say is that I will just maybe write take you to the mathematical expression, you will understand. So first understand, here my sum involves the squares of the deviations, okay. So thus we are considering the sum of squares of deviation. So whatever deviation I am considering, I am taking squares of that, and then I am taking the sum of those deviations. So it is something like this, that is what we have to show. We will show that this, if I consider this sum, we will consider the sum summation. So again my frequency distribution I am assuming is xi fi, I equal to 1 to n. That means my x1, x2, xn and f1, f2, fn are given to me. Then I will first write the deviation. So deviation I will take it from an arbitrary value a. So now the deviations becomes x1 minus a, x2 minus a, x3 minus a, and so on, xn minus a. As I said, first you take the deviation and then you square the deviation, take the square of each of the deviations. So then the deviation, square of the deviation will be x1 minus a whole square plus x2 minus a whole square, x3 minus a whole square, and so on, xn minus a whole square. And when I do that, understand that each of whatever I am doing on xi, it is being repeated fi times. So my x1 minus a whole square in the sum is repeating f1 times. So I will write that as f1 into x1 minus a whole square plus f2 into x2 minus a whole square plus so on fn into xn minus a whole square. So when again, as I said, that long sum that I have said, we don't need to worry, we can write them straight away in a compact notation. So how many terms are there? n terms. So, I will take function variable z, which is equal to capital sigma, that is the summation sign, summation over I equal to 1 to n, because there are n terms. And what is the ith term? Ith term is sum of the square of the deviation, which is xi minus a whole square, and fi multiplied to it. So, therefore, this is equal to fi into xi minus a whole square. I have constructed a sum of squares of deviation from the point A, and I have to establish that this z is indeed minimum when my A becomes x bar. So, that means what I have to show? I have to show that capital A, when I take capital A as equal to x bar, then this value of z is minimum. And what it means, besides that, what it means if you take any value other than x bar, then this sum will be always bigger than the value that you get on taking A as x bar. This z becomes minimum at A equal to x bar. That means this sum becomes minimum at A equal to x bar. So, again I will start with this z, and you must have done till 12th class the principle of maxima and minima. This is a function involving variable x and involving A, so, and also f. So, what I will do is, we will have to establish that this z is minimum at A equal to x bar. In order to do that, I am going to apply a principle of maxima and minima. Where what is the principle? The principle of maxima and minima says that this z that I have constructed will be minimum in A if these two conditions are satisfied. That is, if I partially differentiate z with respect to A and equate it to 0, then I get the point at which z can be maximum or minimum. And further, if this, when I partially differentiate del z by del A again with respect to A, that is del square z by del A square, if that comes out to be strictly greater than 0, then I am sure that my z is minimum at A equal to x bar. So, that is what we are going to show. So, therefore, we proceed with first finding the expression for the partial derivative of z with respect to A. Now, when you partially differentiate z with respect to A, then I hope you remember, we can take the derivative inside the summation, and then I differentiate the power of xi minus a whole square, that comes down. So, it will be 2 times summation I equal to 1 to n fi into xi minus a, and since derivative of A is minus 1, so this minus 1 also comes here. So, this is minus 2 times summation fi into xi minus a equal to 0. Now, I will solve this expression. Minus 2 of course can be adjusted with 0. So, I am left with summation fi into xi minus a. Again, as I said, I can always separate it out. I will separate the summation over the two terms separately, and then it becomes summation I equal to 1 to n fi xi minus a times summation fi. Remember, capital A is independent of I, so comes out of the summation. Then this further can be written as equal to, I have already shown that this is equal to capital N into x bar minus a into this quantity, summation fi is capital N. So, this implies that when I solve this, then my x bar becomes a equal to x bar is the value at which z could be maximum or minimum. When I find the second order partial derivative, then I again further differentiate this expression with respect to a, then I get this as 2 times summation fi, which will be 2 times n, and that is all, n is sum of all the observations multiplied with 2, it is a positive quantity, it is strictly greater than 0. Hence, we have shown that z is minimum at a equal to x bar. Thank you.